For the remainder of our time, we're going to focus on something called Newton's law, not one of Newton's laws of motion, but Newton's law of cooling. We're going to imagine we've got a hot cup of your favorite beverage, maybe coffee, maybe tea, maybe hot chocolate, and it's cooling down. It's too hot to drink right now. The question is, how long do you have to wait until it's cool enough for you to drink? Okay, you just put it in the microwave too long or something. It's really, really hot. You don't want to burn yourself. How long are you going to have to wait? You could do an experiment and do some math to figure it out. Of course, by the time you're done with the math, probably it's too cold. But then you could use that for the future. We could let H be the temperature of the coffee. I'll call it coffee, but it could be something else. At time t, H for hot. You gotta humor yourself in some way. So H is for hot. Heat, hot temperature of coffee at time t. You gotta specify units, like degrees Celsius or something, and time is like minutes, say. Of course, we could use degrees Fahrenheit or even Kelvin. Chemists would all say, yes, use Kelvin. And the rest of us would say, oh, no, I prefer Fahrenheit or Celsius. Those are the variables, H and T. Is there a parameter? Yeah, it's going to be a constant of proportionality. The law, so to speak, is that the rate of change of the temperature is proportional to, this is a little tricky, and it doesn't matter what units you use, it's going to be proportional to the difference between the temperature itself and the ambient temperature of the room that you're in. This is making some assumptions, simplifying assumptions, one of which can be realized by actually stirring the coffee. You're stirring it, you're keeping it well mixed so that you don't have to worry about spatial effects. In reality, right, if you don't stir it, the part of the coffee closer to the edges of the mug and near the top are going to cool down faster than the fluid inside in the interior, because heat diffuses. So we're going to pretend we're stirring so that it's kept a uniform temperature. Of course, that's not even reality either, right? But close enough for a good approximation, which is all we're after. You can convert this proportionality statement into an equation as long as you have a constant of proportionality. Leave a little space. Let me write an H minus A, where A stands for the ambient temperature, the room temperature. Should my constant of proportionality be positive or negative? Coffee's hot. If you graph the temperature versus time, it will be cooling down, so it'll be decreasing. The slope, the derivative, will be negative. H minus A, when it's higher than room temperature, when H is bigger than A, is going to be positive. I want that to be negative, so this better be a negative constant of proportionality. Call it negative K. And once again, K itself is positive, so negative K is negative. Somewhat amazingly, this differential equation even models pretty accurately what happens when you've got liquid that's warming up, as long as you keep it well stirred. Let's not say it has ice in it, right? Because that complicates things. Because when ice melts, that takes energy and it doesn't affect the temperature as much as you might hope. It probably messes with the model. The model's probably no longer accurate. So let's assume it's warm enough that there's no ice in there, or yeah. cold water, but not icy water. In that case, H would be less than A. What's room temperature? About 22, 23 degrees Celsius. I'll assume it's 22. Got cold water, it might be 3 degrees Celsius. 3 minus 22 would initially be negative 19. Negative times negative is positive. Slope of the warming up water would be positive. This one equation characterizes both cooling and heating. Is the simplest kind of model. Again, not saying it's perfect, but it's reasonably accurate. So therefore, we could actually call it Newton's law of heating and cooling. And some books do that. Or maybe heating or cooling, or heating slash cooling. There's lots of different names you can give it. Okay, so what do we want to do now? We want to solve the differential equation. This is one step up in complication from an exponential decay or growth. So we are trying to develop flexibility to handle some complications here. K and A are the parameters, fixed numbers, based on a given room. And the K is probably dependent on the mug, or maybe the liquid itself. Is it really coffee versus kerosene? No, don't drink kerosene. Okay. K depends on the liquid itself to some degree, and maybe the mug and how insulated it is. Of course, you also have it open. It would be affected by whether you have a cover on it and that kind of stuff too. Separate variables. H and T are the variables. Get the H's on one side and the T's on the other. The only place T shows up is in the dt. Notice I divided both sides by H minus A. I did not like subtract H from both sides. In fact, I also did not add KH to both sides, because doing so would lead to a problem. If in looking at this equation, I thought I had to separate variables by adding KH to both sides to cancel on the right and get a KH on the left, that would still be a problem, because when I quote unquote multiply both sides by dt, it would cancel there, but it would not cancel when I multiply dt by KH. That's a problematic. Divide instead by the entire quantity H minus A. Now it's in a form that we can integrate. On the left, you do get natural log of whatever's under there. And you don't really need to use substitution here because the coefficient of H is 1. You could always check it by differentiation. We don't need a constant of integration there because we'll put it on the right side. And let's call it C1. My goal is to solve for H. I get rid of the logarithm by exponentiation. So I get the absolute value of H minus A is e to the C1 times e to the negative KT, which I'll call C2 e to the negative KT. Then get rid of the absolute value signs, and now I'll just call it C instead of C1 or C2 or even C3. Almost done. Now add A to both sides. H equals A plus this. Let me also use my function notation, phi. I'm going to do one new thing, even compared to a half hour ago. I'm going to give this function name a subscript. I like doing this. Not everybody does this. The subscript is going to be the initial temperature, H naught. It's a function of T. I have to figure out what H naught is, though. H naught is a given temperature, maybe, I don't know, 160 degrees Celsius right at the start. No, that'd be way too hot. Okay, that would be boiling. 60 degrees Celsius at the start, which is, I don't know, 140 degrees Fahrenheit or something. I can solve for C in terms of H naught. H naught is going to be phi sub h naught at time 0. That's going to be a plus c e to the 0, which is a plus c times 1. So c, subtracting a from both sides, is h naught minus a. And therefore, my final answer for the solution of the initial value problem is h equals phi sub h naught of t equals a plus, replace c with h naught minus a. Lots of letters. This is a big part of applied math, is being able to handle lots of letters. 2 letters are variables, t and h. All the other letters, the a, the h naught, the k, and even the e, are constants. Though the e is a true constant, whereas the other constants are parameters that, why do we use a special name? It's just that it allows us to think about different situations. They are constants that can change, even though that sounds oxymoronic. This is a lot of power, mathematical power. We've really solved infinitely many problems at once. In one fell swoop, we've solved infinitely many problems. Wow, that's powerful. What might we want to do with this? We might want to use it to figure out when we can drink the coffee. So now use particular numbers. Say we know that the initial temperature of the coffee is 60 degrees Celsius. The ambient temperature of the room is 22 degrees Celsius. And K we don't necessarily know unless we have one other piece of information. Maybe we know that after 1 minute, the coffee is cooled to 55. Maybe phi sub h naught of 1 is 55 degrees Celsius. That would help us figure out what K is. Using this information, h is going to be phi sub h naught of t, which will be phi sub 60 of t, since h naught is 60, will be 22 plus, in parentheses, 60 minus 22, e to the negative k times t. Then use the other piece of information to figure out what K is. We have to solve that equation for K. Subtract 22 from both sides. Then divide both sides by 38 and take the log of both sides. Negative K is going to be the log of 33 divided by 38. So K itself is the negative of natural log of 33 divided by 38, which by properties of logarithms is the same as log of 38 divided by 33. You don't believe me? I'll show you here. Negative ln of 33 divided by 38 is 0.14108. So is ln of 38 divided by 33. Properties of logarithms, 0.14108 approximately. One more equation to solve. When is it cool enough to drink? Depends on how cool you want it to be. Maybe 35 degrees Celsius is good enough. That's probably too cool for some people. Maybe too hot for others, I don't know. Find T so that phi sub 60 of T equals 35. One more equation to solve. 22 plus 38 e to the negative 0.14108. Now I'm using K times T equals 35. Subtract 22 from both sides. Divide both sides by 38. E to the negative 0.14108 T. 35 minus 22 is 13. So we get 13/38 there. In the end, T is going to be natural log of 13 over 38 divided by negative 0.14108, which is a positive number. And again, I could use a property logs to also write this as ln of 38 divided by 13 divided by positive 1.14108. What is it? I want to know. ln of 38 divided by 13 is that divided by 0.14108. It's about 7.6 minutes. It's going to take about 7.5 minutes close to get down to your drinkable 35 degrees. Let's relate all this to slope fields. Let's go back to the differential equation. dH dt is negative k times h minus a. I could give this expression on the right-hand side a name. How about f of h? It's got parameters in it, k and a. I could call it f sub k comma a of h, but that's a little overkill. What did we do with this kind of thing when we thought about slope fields before? A slope field is in the plane defined by the variables, in this case, t and h, where at each point in the plane, you imagine making line segments, small line segments, with slope equal to the value of this function at that point. However, this function doesn't depend on t, does it? There's no t's there. So what does that mean? That means along any horizontal line for a fixed value of h, but any value of t, the line segments are all going to have the same slope. Start with the simplest case. Start with the horizontal line where h equals a. If I plug in a into that, in place of h, I get 0. So along the horizontal line at h equals a, wherever that is, 22 degrees for our coffee, your line segments are all going to be horizontal, having a slope of 0, and that's going to mean there's a horizontal line that's a solution of the differential equation. We gave it a name last week. I'll remind you, it's called an equilibrium solution. EQ sol means equilibrium solution. I don't have enough room to write it all out, but maybe you want to write it all out. Equilibrium solution. When the coffee's at room temperature, it's at equilibrium. It's not going to change. On the other hand, if H is bigger than A, cooling coffee, F of H in value is going to be a negative times a positive, giving you a negative. And the slopes that I make will all be negative in slope. The line segments will all have negative slope. Close to 0, listen carefully, close to 0 when H is close to A. So there'll be negative slope, but just barely. Getting further away from 0 as H gets bigger. And once you're big enough, it's going to look like they're practically vertical, even though they're not. Solutions have to follow the slope field. So your solution curves are like this, which is the kind of graph I already drew, depending on what your initial H naught, initial temperature is. On the reverse side, if H is less than A, F of H is negative K times H minus A is a negative times a negative, giving you a positive. So all the little marks are going to have positive slopes, just barely positive when you're close to A, getting more and more positive as you move further away from A, and constant in slope along horizontal lines. Solutions increase toward A. That's representing cold water that's getting warmer. When solutions move toward an equilibrium solution, nearby. It's called, in fact, not just an equilibrium solution, but a stable equilibrium solution. The idea of stability is that if you, the official word is perturb, if you perturb the system a little bit, meaning, I don't know, drop in a candle into your coffee that's on fire, drop in a little bit of fire, or else drop in an ice cube, you've changed the temperature a bit, but guess what? It's going to go back toward equilibrium. It's stable. A higher dimensional analog of this that's very important, and I emphasize this a lot in differential equations with linear algebra, is like a pendulum. Can't do it high enough to get myself in the picture here. Swinging back and forth. And maybe instead of attaching it to the ceiling, attach it to the wall so that if you give it a big enough push, it can go around the horn like that for fun. If you do allow such a thing, there is actually two equilibrium solutions. One representing pointing straight down, one representing pointing straight up. The one pointing straight down is stable. Give that pendulum a little flick, and it goes back to still heading straight down. The one pointing straight up is unstable. Assuming you could get it perfectly pointing straight up, which you probably can't, if you gave it even the tiniest little flick, it was in a vacuum, but then a stray oxygen molecule came in the vacuum, or hydrogen if you want to be extreme, and hits that thing, it's going to start moving. It's unstable. Stable equilibrium solutions have nearby solutions going toward it. You can have unstable equilibrium solutions, and you can even have both. For example, you could have a situation where you've got two equilibrium solutions here and here, and maybe, oh, let's say this one's stable, but the other one is unstable. Solutions go away from it, including these that are in between. This is a stable equilibrium solution. This is an unstable equilibrium solution. Again, I make a real big deal of this in differential equations with linear algebra. How do you figure out whether a solution's stable or unstable? You can make the slope field. There are also techniques that allow you to decide even without making a slope field. And maybe I'll talk some about that on Wednesday.